let's see, we're done with fluids. The homework for fluid is out. I can't even talk. My mouth is so cold. My finger's so cold. So I need everybody to just kind of breathe a lot or move and heat this room up. I got this out. This is a heater. This is how heaters used to work. If you touch this, you get both burned and shocked, right? So things were not as safe a long time ago, but I need it for my hands because I can't write right now. So we're done with fluids. The fluid homework is all out and done. So it's like 15 questions, and it's due a week from yesterday. And now we're moving on. We did simple harmonic motion last time, so we're going to finish simple harmonic motion today and get to waves. So we're just doing the interesting parts of everything. I'm sure that laughter was at something else. Okay. So quick review of what we said last time about simple harmonic. Only a physicist would use the word simple like that, just to be insulting. Oh, simple, right? So you have something heavy. So you got a mass on a spring. We said, oh, let's solve the equation of motion for that. We wrote Newton's second law. And we realized it's a differential equation, and we guessed the solution, and we plugged it in. We did all that stuff. And we got that the answer, the position along the x-axis as a function of time was a sinusoid. Sine omega, I'm going to start writing omega naught, t plus phi. We said this is the answer, and there's really three parameters there. Right, this is the position as a function of time, so independent variable, dependent variable, and then three parameters. Omega naught is the angular frequency, and we showed you, we did a little shadogramming to show you that it's the same as the omega in circular motion. It's just in radians per second. A radian can be a trip around a circle, or a radian can be a trip through a cycle. A cycle and a circle are the same. Is that going to fall? Maybe. So that's the angular frequency omega, and for an oscillator, we call it omega naught because we also call it the natural frequency. And that depends on properties of the system, the spring constant and the mass. Then these other two, the amplitude, right, A, and the phase constant phi, those really don't depend on the properties of the system. Those can vary, right? Those depend really on the initial conditions. If I launch this with a large amplitude, A is big. If I launch it with a small amplitude, A is small. And the phase depends on when I launched it, right? So that's why that's the difference. So that was our solution. We were all excited about that. And we said, what can we do with it? Well, we can write V, the velocity. And one thing I didn't quite label last time that is useful in problems, we just took a derivative and said sine goes to cosine, and you pull out an omega. But what we didn't really say explicitly is this is often referred to as V max. This is my cursive V, by the way. That is the amplitude of the velocity, right? The velocity also varies sinusoidally, and it goes from maximum up to minimum down, max up, min down. So the amplitude of that expression, A omega, is V max. And if you really want to get into connections, this kind of looks like if this were a radius and it were circular motion, the tangential velocity is radius times omega. But when we have cyclical motion, the velocity is the amplitude times omega. So similar ideas are flying around. And then we also could write down the amplitude as a function of time minus A omega squared back to sine omega t plus phi. So we showed that as well. And again, you could say, well, this is the maximum acceleration if you wanted to think of it that way. And you could say, oh, it's also kind of like the tangential acceleration was the radius times omega squared. Oh, yeah, kind of the same thing. Okay. So just quick review in case you weren't here. What does the word say ensued the orathithes next to cos? So I don't think I have any room to talk here. This is omega t plus phi. I guess that's not a word. It's a word to me. All right. That's a V. Okay. And then the main thing that the thing I was trying to do to connect it to the exam was we looked at the total energy. And we said the total energy was 1/2 k a squared. We said we could get it from the kinetic. We said the maximum was 1/2 m v max squared. Bunch of stuff cancels and you get this. Or you can get it from the potential of the spring. The biggest potential you have is when it's at a turning point. The biggest compression of the spring is A, so your potential will be 1/2 Ka squared. And we saw how it basically just goes back and forth between kinetic energy and spring potential energy. As the thing moves up and down, it's going between those two forms of energy, kinetic and spring potential. Although when it's upright, there's gravitational in there too, but don't worry about that. Okay, so that was it. That's where we were with masses on springs and simple harmonic motion. So we've got to do the classics. So we've got to talk about the second kind of simple harmonic motion that is so important. What is the phrase between the x equals equation and the omega naught? It's the cold. My fingers are literally numb. It's like I'm writing like this. Like I can't feel any fine motion of my hand. Oh my God. What is the phrase between x equals, I don't know, a sine omega naught t plus phi? I'm not sure what phrase you mean. Yeah, we'll get it later. Okay, so another kind of simple harmonic motion is the pendulum. All right, we love pendula. Is a mass on a string. See the little one-letter difference there. A mass hanging from a string is a pendulum. And of course, the pendulum we care about right now is the big one that hangs from the ceiling. Let me get everything else out of the way, so we don't want to have any disasters here. Oh, we don't want to hit this thing. I can't move. Oh, I don't know what to do. Okay. Okay, so the pendulum is basically just a big heavy mass hanging from a light string, and we watch it go back and forth. And just if you watch it go back and forth, you can definitely get a feel that it's simple harmonic motion, right? It feels kind of sinusoidal like that. So let's draw our pendulum. Our standard pendulum looks like this. You got a mass here and theta there. And it's got some length L. And it might be moving at some angle. The angle is changing back and forth. The angle 0 here, angle goes positive there and negative there, or vice versa, right? So what we want to do is look at how are we going to derive an equation for this motion. Is it going to come out the same? Is it going to come out different than the mass on the spring? How's it going to work? So if you read about it in a book, it's very confusing, okay? So I'm going to clear it up, maybe. It's confusing because one is they try to warp it into like an XY problem, and then they make a reasonable mathematical approximation. So there's two things happening, okay? So the first one is trying to warp it into some translational problem, and that's a really bad idea, right? So what they're doing is sometimes people will say, well, let's just think of it as though it's only moving in the x direction and do some approximations. Well, based on what you learned in the last exam, if this were only moving in the x direction, would it go back and forth? It wouldn't, right? Because the whole point of an oscillator is it exchanges between potential and kinetic energy. So if it's not going up, there's no potential energy to drive it, right? The whole reason this is moving is because of gravity. It's not the tension, multiple choice 5, right? It's gravity that's pushing it up. 2 people haven't taken the exam yet. Never mind. It wasn't really number 5. It was, and the answer is tension. I don't know. So now I've confused them and they don't know what to think. I love spaghetti. Okay, now they're really confused. It's moving up and down because of gravity, so we can't say it's only moving x and y. Okay. And then sometimes a book will say, let's treat it in the tangential direction, but apply Newton's second law like we normally would. Well, the problem with that is you're saying, let's take a curved surface and treat it like a Cartesian axis. Well, you can't do that either, right? That's not a good idea either. But you do it and you get the right answer. So that kind of sucks, right? So we don't want to do that. We want to do it the right way because we're all so smart, right? You guys are so experienced. We spent like 2 weeks on rotational motion. So why don't we treat it like a grown-up, like rotational motion? It's actually easier than all the crazy approximations they do to try to say, well, let's just think of it as tangential. Right? There's no need to do that. Okay? So if we're going to think of it as rotational motion, what is Newton's second law? Here we go. It's okay. It's going to be good. It's going to be good. Sum of the torques is I alpha. Oh, trust me. Trust me. It's better. Okay? So we got to say, okay, we got to think about the torques and what's going on. Let's do a free body diagram. Here's my mass. Here's mg down. and tension that way, tension force that way. Right? Trust me, it's better. It's better. Okay? What's the sum of the torques? We need the torque due to each force. And you say, oh, I got to do components. No, you don't. You don't have to do components. Right? If it's a torque, where the first thing with any torque problem is you define the axis of rotation. Right? There's the axis of rotation. So you say, I need to draw the R vector because it's from the axis of rotation to where the force is applied. Right? So let's draw that R vector like this. It's a vector down the string at some angle theta. Its magnitude is L. We could call it the L vector if we wanted. Right? And now let's draw the force vectors all tail to tail. Right? Because remember, torque, you draw the R, the displacement vector, or the position vector, tail to tail with the force. So the two force vectors look like this. Here's mg straight down, and there's tension that way. Right? Not too horrible. That is the two force vectors along with the displacement vector. And now we just calculate the torques. Right? What's the torque due to the tension force? Oh, well, it's magnitude of L times the magnitude of T times the sine of the angle between them. So it's 0. Right? Whenever a torque is right along a line that goes to the rotation, it's 0. The sine of 180 is 0. Plus, now let's do the torque due to mg. Right? Well, it's L is the length, or the length of the R vector. Mg is the magnitude of the force, and the sine of the angle. Well, that angle right there, it's directly theta. Look, you don't even have to do components if you do it this way. You don't have to think, what's the tangential force component, mg sine or cosine? You don't do that. It's a cross product. By definition, you have a sine here. And now here's the tricky part that'll get you. Is it theta? It's negative theta. Oh, because you go from R to mg, and that's clockwise. So you would have to notice that you put a negative theta there. The chance of that affecting a problem is not high. We mostly do magnitudes. But if you want this to work out, it's good to put a negative sign there. Then you say, okay, the torques, that was fun. What about the I omega? What is the moment for a mass going in a circle? mr squared, right? M, what's R? R is L, ml squared. Okay. And then what is alpha? Alpha is the second derivative of theta with respect to time. d2 theta dt2. Okay. So then you say, okay. So then we'll simplify it. This was 0, right? That was sine of 180 is 0. Sine is anti-symmetric, so the negative sign comes out. And then let's see, m is going to cancel, L is going to cancel. All right, I'm going to keep this over here. I'm going to bring this over here. And I'm going to say, there's my negative sign minus g over L sine theta equals, and over here we have the d2 theta dt2. Okay? So this is what they're doing in the book, right? They're doing some approximation to try to say, well, it does this, and you get an expression that looks kind of like what we had for the mass in the spring. Remember the mass in the spring, we had something like, d2y dt2 equals minus k over my, or whatever it was. That's probably wrong. Okay. Off the top of my head, I'm screwing it up. But we're just trying to get this equation again, this equation that tells you something is oscillating. Okay? But this isn't it. If we had to solve this, so that was the first part. That was the dumb approximation. We now fixed it. Instead of doing something with tangential motion or calling it flat, we said, no, we'll do it rotationally. So now we're here. Okay? So now to solve this differentiation equation will be really hard, because we have to say, what function, when you take two derivatives, equals the sine of that function? And there isn't one. Okay? We can't solve that, right? There's no answer to that. So now we have to do the small angle approximation. Sine of theta equals something special when theta is small. So if you get out your calculator and you turn it sideways so that you actually get the sine functions, and then you put it in radians, and you take the sine of 1 radian, you get 0.84. But 1 radian's a lot, right? A whole circle is 6.28 radians. So let me take this 0.1 and take the sine of 0.1. 0.099. When I put in something small, I get the same number back. What about 0.001 sine? 0.000999999. 0.001. So when you take a really small number in radians and take the sine, you get the same number back. What if I put my birthday? 0.0424771. And I take the sine of that. 0.024707, it rounds up to 1. Okay? The sine of a small number equals the number. Right? Sine theta equals theta if theta is, is less than 1. A lot less than 1 if it's small. Okay? But you got to do it in radians. You can't do it in degrees. Okay? I could show you why that's true if we do a bunch of sines and cosines. It's pretty cool, but let's move on. I'm starting to learn what's cool to you. Okay? Getting excited about sines and cosines, things have changed. Okay. So if that's true, then we could say, approximately equal, Then we could rewrite this and say, let's rewrite this and say d2 theta dt2 equals minus g over L theta. And now that looks exactly like the equation for there's a negative here, the equation for the mass in the spring. The second derivative equals some constants times the function. Okay? So this is what physicists get unrealistically or sort of over the top excited about, is they try to find like one kind of equation where a lot of things lead to the same equation, and that explains why everything behaves the same. The reason the mass on the spring moves in a sinusoidal fashion, and the reason the mass on the string moves in the sinusoidal fashion is because they both are driven by the same equation that has the same solution. Right? That's what's cool about physics. So, that's most of it, actually. That's near the limit. So let's look at this thing and see what we can learn about pendulums from it. That's real quick. All right. Let's see. So, oh dear. So let's look at the solution. Here's another thing about physicists. Physicists are lazy, okay? Once we have guessed a solution to a differential equation and showed it works, we're not ever going to do it again. If we see that differential equation again, we just write down the same solution. Right? We don't do it over and over and over again. So if the solution before was a sinusoid, then I know that this one's going to be a sinusoid. Theta equals theta max, that's like the amplitude of the angle, times the sine. And if I were to guess and plug in and solve for the constants, I would get the exact same thing, or I'd get a new number here, square root of g over L t plus some phase phi. All right. Have you considered investing in a fingerless gloves? Have you considered investing in... I don't get it. Do they keep your hands warm? It's my fingers that are cold. I don't know. I've completely lost track of where I am. Okay, so this behaves exactly the same. This is the natural frequency. I should invest in finger cots, which are little things that only go on your finger, if you've ever seen those in a lab before. This is the natural frequency. So instead of k over m, it's a square root of g over L. Okay, this is the amplitude, basically, in terms of treating it as an angle. It's the angular amplitude. If we wanted the physical amplitude, how far it goes, well, it's just theta max times L. Right? If I wanted to know how far this goes approximately this way, theta max times that length, and then you could pretend it's one-dimensional, even though it's really a curve. And this is also the phase. And again, this is set by properties of the system, the gravity and the length, and these are free. They depend on the initial conditions, right? I can make it go with a big amplitude if I hold it out here, or I can make it go with a small amplitude if I just hold it here. And I can make any time I want be time equals 0, so I can adjust the phase, right? So let's see. So the interesting thing about the pendulum is that the natural frequency doesn't depend on the mass. Okay? Let's see. So I've got the time. Does anybody want to be the timer today? I can do it. Anyone? Time? Here, you time. Okay, what we're going to do is we're going to measure how long does it take to do one period of the pendulum. Here we go. I'm going to try not to hit anything. Ready? Go. And Stop. What is it? You can read it. 5.5 seconds. I knew that's what it would be because I did this before. Now, if we change the mass, so I'm going to put this thing on here. Okay. And here, I'll do it this time, just to move us along. That's excellent work. And now we're going to do it again. And, oh, don't hit my coffee. And 5.5 seconds, exactly the same, right? So it doesn't care, there's no m here. It just cares about g and the length didn't change, right? This says, if you wanted to know physically how far it's going, that's like the arc length s equals theta max, this amplitude times L. I'm just saying in problems, you might not be asked for the angle, you might be asked for like a distance. So it's just going in a circle. So the arc length is always just theta times r. Okay, so what this tells us, this is very important for this person, this technology, right? Spitting everywhere. This technology here, clocks, right? This is how they made clocks in the early days, because you could have something that was something based on time, but was very independent of other things, right? So it doesn't matter what mass you put there. The critical thing was the length, okay? So the first clocks were made by this guy, pretty boy, Christian Huygens, okay? It's not pronounced Huygens, it's pronounced Huygens is the proper way to say it. Okay, let's put pretty boy in his place here. He's around Descartes. And the reason we've gone back to our timeline is what I think is impressive is that Christian built a clock, and it was a standard for timekeeping for 270 years, right? So he invented a technology that lasted 270 years. Pretty impressive. That's like if you invented something in 1750 that they're still using. Not bad, I would say. Not too many things last that long. So this was a major breakthrough, all based on what we just derived, that omega just depends on gravity and the length. Now, let's see. So that's great. So we have two, oscillators. And now we want to think about, and we could come up with more. Basically, lots of physical systems do this. It's not just springs and pendula. Other things do it. But now we want to think about what eventually goes wrong, right? So I'm going to put this here, where this runs into this, right? Wait a minute, hold on. We want to see, basically, does this go all day? And the answer is, of course, it doesn't, right? We put it right here. This could be me. And we let it go. And we say, is it ever really going to hit me? Let's see. And you can see on the first one, it doesn't get very close, right? Oh. It's already missing it by quite a bit. Now let's see, this one is already missing it by that much. It's already that far down. So clearly what's happening is it's not doing this. Right? There's no reason the amplitude would decay here. That should go on forever. So already there's something wrong with our equations. So we must fix them. Right? We can't have them broken. Let's see. So what we have is we have to think about how resistive forces affect oscillators. Right. Resistive forces. The most general definition is they oppose motion. And you may think, I'm in good shape because I already know a lot about resistive forces because we've done kinetic friction, right? Kinetic friction. And what was kinetic friction? It was constant, basically. It just depends on the normal force. So that was an easy one. Oh, unfortunately, that's not the one we use here. Sorry. Another one is air drag. All right. That goes as v squared. This little symbol means goes as. It's not an alpha. It's the goes as symbol. There you go. So kinetic friction constant. Air drag goes as v squared. That's exciting, but we can't solve that equation. So that's too hard. Okay. This one is too easy. This one is too hard. Let's do the one that's just right. Liquid drag goes as v. Right? And this is the one that sort of the equations work out, and it's sort of the universal one. Like I said, we like this because this happens in many other systems. It's a very general phenomenon. Lots of systems oscillate. Lots of systems lose energy, and they do it in a way that kind of as though there's a force going as v. So that's the one we're going to use. I've got to put this down. Look, it's not even close now. Look at this. Look how much energy we've lost. we've lost that much energy. Look at that. Okay, so the way we do it then is we use the drag force. So by this drag force, we mean in liquid usually. It's usually with some surface that's forced to move up and down in a little liquid column. It's called a dash pot. So the drag force we'll call big D minus BV. So it is proportional to velocity, like I promised. B is the constant, the damping constant between the force and the velocity. All right. It's in kilogram per second. It has no special name. You can see what's in kilogram per second. This is kilogram meters per second squared. This is meters per second. So the only thing left is the kilogram per second. Yeah, in kilogram per second. So if we were going to draw it here, let's draw the pendulum here in this position and in this position. All right. Then let's draw all the vectors on it. We'd say, well, I got mg down. I'm good at that one. I got tension that way. Right? I've got velocity. At this point, it's always tangential. Therefore, my drag force is just opposite of velocity. Right? It opposes motion. Minus b constant times v. So there's the drag vector, like that. And when it swings the other way, if we assume it's gone up and come back down, then mg, tension, velocity, drag vector, opposing the velocity. Right? And if we wanted to do some IQ test, tricky question, we could say, here's a pendulum. Which way is the drag force? Can you tell me which way the drag force is? No, right? Not enough information. That's a not enough information question, because a pendulum can be there, and it can be moving this way or that way. Right? The drag force doesn't always pull it down. The drag force always opposes motion. So you have to know which way velocity is to know which way the drag force is. Drag force could be 0. If this is the turning point where it stops moving, then there is no drag force. Right? It's only due to motion in a fluid. Okay? So now, we're going to add that drag force that is slowing down the clock to Newton's second law. Right. Now, we're not really going to be doing these things anymore, right? So we saw the first time we did Newton's second law for the mass in the spring in great detail, got the equation of motion, we guessed an answer, blah, 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 blah. For this one, Newton's second law, we got the equation. We didn't guess an answer, we just gave you the answer, right? Okay, now let's just write the equation. We're not even going to bother, right? So now if I were to add the drag force to Newton's second law, we get something that looks like this for the mass in the spring, or for any oscillator. Yeah, this is in terms of a mass in a spring. d2x dt2, that acceleration part, that's the that's the ma part. You'd get b over m times the velocity, right? And then you would get k over m times the position. So this is close to how we wrote it before. I think we had this on this side negative. So this is the ma, this is the kx part, but now this is the new drag part. Okay? It's not negative just because we've moved things from one side to the other. But this is sort of the general equation that you get. And then you guess a solution, you plug in, etc., right? It's a little bit harder guess. What function when I take two derivatives and then I add a constant times the first derivative and then I will have a constant times the function equals 0, right? That's a little harder to guess, right? But you use a little intuition and you can get that the solution is similar to last time. We just put an exponentially decaying part in it. A e to the minus b over 2m times sine or cosine, it doesn't matter, omega t plus phi. Right, that's the damped oscillator. Just like that. Okay? Let's see. Now there's some interesting things about this damped oscillator. You can say it looks just like the other one, except now the amplitude is decaying, right? So we could say, one way to analyze it is say the amplitude decays. So you could think of it as the amplitude as a function of time. Right? Basically this part. Oh, there's a t missing. There you go. The amplitude is a function of time is sort of like you could say, how do I want to say it? It's like A naught, the original amplitude, e to the minus b over 2mt. So we'll do some exponential functions in a minute, but if you can probably visualize what that looks like. You start at A naught, and it comes down. Just like what's been happening here. Our amplitude was out here. What happened, right? Now it's all the way down to there. There's our amplitude. We lost that much. It's not moving in a liquid, but still, it's a resistive force slowing it down. One other little thing happens when you go plugging things into here is that the omega is slightly different, okay? So that's why with no damping, I like to call it omega naught. This is the natural frequency where it wants to go. But if you have damping, your omega comes down a little bit. It's the square root, in this case, of k over m minus b over 2m squared. Like that. Comes down slightly. So the units work out. Do we need to be able to find x on our own? If yes, what are some strategies? No. Yeah. You're not going to have to guess x. You're not going to have to guess a solution to something like this. This is just for enrichment. Okay. That's like differential equations, and we've now done the only two that you can guess. So there's none left. But I just wanted you to see that's how the same process happens every time. You apply Newton's laws, you get an equation, you come up with a solution, you plug it in, and then you get the full solution. So we've got this amplitude now. This is free, and this is decays, just like you're seeing. The frequency is reduced, but it's very small. Like if you look at typical numbers, it comes down by like 1%. So you can't really tell the difference, usually. If the damping is really big, then it might not oscillate. So there's whole ranges of interesting behavior here we're skipping over. We're just talking about the typical sort of lightly damped system. But mathematically, this comes from plugging this into here, basically, and solving for omega. Okay? And now if we wanted to plot it, it would look like, let's see this. All right, so, well, I did a sine, so I've got to start here. But it's got some big amplitude, and the amplitude just goes down like that. All right? That's not a good drawing, but that's horrible, actually. But that's sort of roughly what it would look like, except it usually have a lot more cycles than that. So this is x versus t, the position versus time. And you can kind of draw this dotted line like this. It represents the decaying amplitude. Represents this thing, minus e to the b over 2mt. Right? So just visually, that's what it looks like. I keep setting my phone down. Yeah. Okay. Okay. Yeah, okay, so we'll stop now. We'll do a sample problem of that in a minute. So much to cover. One question I got is, when is the fluids homework due? Next Monday. Got a whole other weekend for fluids. And then the final homeworks are all due the last day of class, because God knows when I'm going to scrape them out. So here we go. But the last ones will be about, I'll get them out as soon as I can. Simple harmonic motion and waves. Our last problem. So what I want to do real quick is do a sample problem and show you how to deal with these decay problems. A lot of them will be pretty standard. This oscillator has these properties. It's not damped. Just go use the equations and some physical intuition. But there's one kind that I think is a little confusing, one kind of problem that relies you really understanding exponential functions. So I thought I'd do one of those. So let's look at an example of an exponential decay problem. All right, there we go. And the idea that I'm trying to get you to understand is you don't need the details often. Need the details. Okay. So let's say, here's the problem. Let's say, I don't know how to specify this as the problem. There's a star. An oscillator with mass is 2 kilograms. Right, hilarious. And constant, and B is 0.01 kilograms per second. And the question is something that sounds like you don't know enough, right? How long to lose 1/2 of the amplitude? You don't know the amplitude. You don't know the mass. You don't know how this thing got started. You don't even know that it's a mass on a spring. It could be a pendulum, for all you know. You know nothing, right? But you can still solve the problem. That's the amazing thing, is you can still solve the problem. Because we can describe the amplitude as A equals A naught e to the minus bm b over 2mt, right? No, yeah, with the mass. Yeah, you have to have the mass. Yeah. You don't have the spring constant. You don't have the length, is what I meant. If it was a spring or a pendulum, you don't have some properties. So what we can do is just say, well, we know that it decays like this. And you got to know a little bit about exponential decay. If we're plotting the amplitude now, and this is time, then at time equals 0, that's when you have your maximum, A naught. Okay. Just plug 0 into that equation. E to the 0 is what? 1. Right? So that's when A equals A naught. So this is what exponential function decays look like, except they look more like a real one. Like that. Oh, wow, that's perfect. Frame it. So the question then is, when does it get to halfway down? Well, I don't know the amplitude, but I know what half the amplitude looks like. It looks like that. So we're really just asking for when does this happen? Okay. T star, you could call it, or T half, the half-life, or whatever you want to say. So really, you just need to know how this thing curves down. You don't need all the details of the motion if it's an exponential problem like this. So what you would want to say is when, how long to lose amplitude, lose half amplitude. So I'd say, when does that happen? So it's kind of like in kinematics. When we ask when something happened, we made the something happen mathematically, and we called it T star. And we just solved for T star. So it's that kind of a thing. So we have the amplitude as a function of time. When does it equal A naught over 2? When does that happen? Well, say, okay, A naught over 2 equals A naught e to the minus b over 2m t star. You know, this is the special time when it equals A naught over 2, not just the whenever it is a function. And then mathematically, that you can deal with, maybe. Get rid of the A naughts. Hey, we don't need the amplitude. Look, it goes away. When you're asked for a fraction of the amplitude, you put it on both sides of the equation and it's gone. Then you're left with 1/2 equals e to the minus b over 2m t star. So you just solve that for t star. Right? Oh, we can do it. I know we can do it. So how do you get rid of an exponential in an equation? Yes, you take the natural log of both sides. Wow. You guys are so expressive. Ooh. Did y'all learn to say lawn? You didn't? Okay. So it's cool. You don't have to say natural log, you say lawn. So I was raised to say lawn. So you take the lawn of both sides. So the lawn of e to the minus b over 2m t star is just minus b over 2m t star. The natural log of 1/2 equals minus b over 2m t star. Right? And now, if you are exponentially inexperienced, and by that I don't mean it's gotten a lot worse, I just mean you haven't done a lot of exponents, you're going to panic and think, oh, I'm going to get a negative number, oh no. Oh, but if you're exponentially experienced, you say, oh, look at that. Boom, negative gone. Right? The log of a negative, you flip it over or something like that. I think that works. And you do all this, and you plug in numbers, and you can get a number. Right? We're down to just numbers now. We were given b, we were given 2m. I know the natural log of 2 because I have a calculator. And you get 277 seconds. Okay. So there you go. So you solved it without having the details. So I just want to make sure if you need to be a little bit familiar with how these exponential functions work. Okay? And then you can also do detailed problems. You could solve for the amplitude at any time t, or whatever. Now you're thinking, is this important in my life? And the answer is it is. This is the reason for something that impacts you a lot. Well, maybe not you, but your forebears. Is if this thing decayed this fast, how did these clocks dominate technology for 270 years? Right? Clearly, they have to be driven. But how do you drive it and have it go at the right frequency? Because actually, if you drive a motion, it goes at the frequency you drive it at. It doesn't go at the natural frequency. So this is the kind of thing that does it. This is the escapement. So you can see this is the pendulum going back and forth here. And this is what Huygens invented, right, that made it work. This is the pendulum going back and forth here at its own frequency. And this is the thing that you wind up, or that has the two big masses on it, like at your grandparents' house. You know, you pull it this way, and then it slowly pulls it back. Or with springs. And this thing is just wound and ready to go, but you can see it's applying a force. I can't time it. Now, right? It's like pushing it on that side and pushing it on this side, but it doesn't push until this decides it's time to get there. Right? So this thing, the pendulum, is still setting the timing of the motion, and this is the thing, though, that's giving it a little kick to keep it going. This is what they'll tell you is happening at the Houston Museum of Natural Science with the Foucault pendulum. Okay? This is the big thing. This is the reason clocks tick, is this mechanism, right? Do you hear this thing ticking? Shh. No, it's not ticking because it's not being driven. It's not stopping. This is the reason clocks tick, which is a huge impact on society and the culture and all this stuff. So TikTok was like the robot, and those are the robots, of course. I love Kesha. I'm sorry. I am pretty sure that Kesha is a misunderstood genius. I'm serious. She is definitely a misunderstood genius, and I don't think she's going to get anywhere because she's too misunderstood. But I'm quite certain that she is a genius for many, many reasons. Okay, so now I was hoping someone would say, why is there a 2 there? Surely someone is concerned about the 2. Right? Physicists were so brilliant. Why would we derive and define B such that there's a 2 in the equation of motion? Wouldn't we want to get rid of the 2? Can't we define it differently where there's no 2? So here's the deal. So we are good at defining things. For convenience, we define a time constant. Basically, you can see that B over 2m is a time constant. That's what sets how fast this decays, and that's why it's the important number when we're solving a problem. But often we define the damping time constant as put those together. And we call it tau, and it's equal to m over b. Okay, not b over 2m, not 2m over b. We call it m over b, because that gives us something in seconds. So I'm telling you this because the book will talk about it. Sometimes problems will be in terms of a time constant, like on the MCAT, right? They may not give it to you. They might not tell you the value of b and m, and you calculate the time constant. They would just say, this is the time constant. Okay, they're trying to give you the time constant. So the factor 2 I meant to talk about was really here. Why don't we put a 2 in there so that it just turns into t over tau, right? Why do we have it as t over 2 tau? That's what's weird. So we've looked at this. We've looked at the amplitude. Right, we would say A equals A naught e to the minus, and if it's B over 2mt, it's 1 over 2 tau t, right? T over 2 tau. So that's where the 2. Why would we leave a 2 in there? Okay, why 2? I didn't mean to start talking about it so early. Now I've got like an obsession. Right? Why the 2? Okay, and the reason is we care more about energy. All right, so let's look at the energy decay. This is something we could ask you about. The energy decay looks like this. Well, it's 1/2 Ka squared is the energy, right, the total energy. So if the amplitude is slowly decaying, the total energy in the system is also decaying. I mean, you're losing it to heat due to the friction forces and due to the damping. So, so when it was undamped, just as a review, I'm not in sync with what I'm saying and writing here, E was 1/2 Ka squared, and it was constant. Remember, it was going between kinetic and potential. No, kinetic and potential. But now that it's damped, now we can write the total energy as a function of time, and we can see that it decays. It's 1/2 K, and now we have this decaying amplitude in there, A naught. A naught e to the minus 1 over 2 tau time squared. Okay. And maybe you can see what's going to happen. What happens when you square A naught? You get A naught squared. What happens when you square the exponential is you double it. The 2 comes in here and it cancels that 2. So that's why we define it this way, is what we care about is energy. So, and then you could even be really clever and say 1/2 K A naught is E naught. Whatever energy it had at the beginning exponentially decays at tau, e to the minus t over tau, like that. So that's why we define it that way. As we think in terms of energy, waves we're doing soon are treated in terms of energy. So that's tau. Okay? So a problem might give you B and M, it might give you tau, whatever. Now you know the how they're related. Okay. Well, we could do a problem with this. It'd be exactly like this one. We could have said, how long until the energy decays to lose 1/2 its amplitude? And you'd go through the exact same math, except this 2 wouldn't be here. That'd be the only difference. So the amplitude and the energy decay at different rates, and that's because the energy depends on the amplitude squared. That's why they decay at different rates. And this is an idea fundamental not just in oscillators, but in waves and in everything. Anything shaking, the energy depends on the amplitude of the shake squared. Even if it's not in meters, whatever it's in, that's in general. Shaking things have an energy that goes as the shake squared. Okay? Okay. Waves. So now we get to go to the most exciting thing. It's waves. Okay, so we're done with oscillators. I only did one sample problem. There'll be good ones on the homework for you to practice. But we want to get to waves because this is where stuff gets interesting and important here. Let's see. So let's see what we can say about a wave. Waning minutes. Let's see. So new chapter, wave. Let's see. I would say the simple definition is how a disturbance, and by a disturbance I really mean energy in this case, and here's the part that's new, moves through a system. Nothing has moved through any system, a medium is what I meant to say. Nothing has moved through anything yet. All right, so far in this class, nothing has moved through anything. We started with point masses, then we let the masses have a size so they could rotate, then we let them deform a little bit, and we kind of pushed on one end of a fluid column and the other end moved. That's sort of a disturbance moving through. But now we're going to think of something beyond just those simple masses. We're going to think of a medium that has different properties at different points in space. Okay, that's kind of the idea. But let's look at a few examples. Let's look at the disturbance. Right, the disturbance over here and the medium over here, and then you can guess the wave. That'll be the fun part. All right, so the disturbance is pressure, and the medium is the air. What is the wave? 1, 2, 3. Sound, yes. So sound, everything you've been listening to is me vibrating the air with my larynx, maybe? Yeah. Vocal cords, yeah, vibrating the air. Vibrates in your ear. Ow. Okay, that's been happening all semester. Sounds a little intimate, actually. We could have the disturbance be the height of water. All right, what kind of a wave is that? It's a wave. Dude. All right. That's how you pronounce that. Wave. Okay. We could have the disturbance be the deflection of a string. That's the one we're going to do. That's called, what's the word when it's the quintessential one that everybody does? I forgot the word. Okay, we're not going to name that one. We'll do it in a minute, though. And then we could have a disturbance of the electric field. Ooh, getting into next semester. In space. Does anybody know what a disturbance of the electric field in space is? Electromagnetic wave, which is light. Right? Light is just a wave of the electric field through space. I think I want the word canonical here. Your first wave is the wave on a spring. Now, a new wave was discovered and won the Nobel Prize like 2 years ago. The gravitational acceleration in space. All right, that's gravity waves. Because of the kind of interaction gravity is, we know it should have waves. They're just really hard to detect because they're so weak. So it took until just a few years ago for them to actually detect them by having some little system so sensitive that when a black hole blew up somewhere, it made enough of a jump that the system could detect it with 2 interferometers in Europe somewhere. I don't know. Okay, it was a big deal, though. Okay, we basically saw gravitational light was this last one. So that's what all these things are. All it is how does a disturbance go through a medium, and what is the physics of it? How do we describe it with physics? And it's sort of like the oscillator that we get excited when all these different ones are described with basically the same equations. That's what we're looking for. That's why we start with a spring, with the string, the simple string wave. Okay, so we're starting with this. Right? So here's a stretched string. So the only parameters I need to describe this string are its length and its mass per unit length and its tension. And then I can describe like a wave. Like if I go like this, see the wave went down, the disturbance went down the string and it came back. Or I can do like a sine, right? And the sine goes down the string and comes back. This is my favorite demo because when you're looking from here, it looks awesome. Right? And you guys are like, he's just shaking a fucking string. What's this? Like, you don't see anything. All you see is just, a string shaking around. But you should see it from here. It's really cool. Okay. Wow. Okay. But you get the idea. Like a disturbance goes down the string. So now what we're going to do is see if we can describe that mathematically here. What's the word next to string? Canonical. I think that's the word I want. I don't know. The classic wave. All right. So let's see what it would take to describe it. Okay. So the string is the medium. A medium is not a body. That's what I was saying before. We aren't just going to F equals ma a particle and get this right. We're going to think of it this way. Like here's a string, and it's between two clamps. Like I was holding it over there. I tied it to this thing over here so y'all can't leave. And we want to describe it mathematically. We would say the deflection is in the y direction, but we have to keep up with everything also along the x direction. It does all these positions in space. So we're keeping up with the deflection in y versus its position in space. And also, it varies in time, right? Because it's a wave. Okay. So we have to consider deflections in y along position in x for all time t. So we have to solve this, y as a function of x and t. That's like the function we're trying to solve for. And we're not going to do it because this isn't sophomore physics. I'm just trying to give you an idea of what we're doing here. So there's something about this that should have you, like somebody should have screamed. You guys are so expressive. There should have been a, oh my God. Look, there's two independent variables. Actually, you just don't even know that you should be afraid yet. That's the deal. You're afraid of something called multi. This is beyond multi. Okay, this is much worse than multi. So basically, this is a partial derivative. A partial differential equation. Oh my God. And you guys are like, yeah, I did those in 8th grade. I know, but still. Most people are afraid of them, okay? Partial differential equation. So harder to solve than regular differential equations, okay? Taking partial derivatives isn't so hard, but solving partial differential equations is hard. Because the thing on the right, the wave equation, is all crazy pants. Let's see. So we're not going to solve it. We're just going to talk about it, okay? If we were to apply F equals ma to pieces of string, we would get some special equation called the wave equation. We'd get this. d2y dx2 equals mu over t. This is the mass density. And this is the tension. d2y dt2. Right? This is the wave equation. We are not driving it. We're not going to solve it. But it can actually greatly enhance your intuition for how waves work. Okay? That's why I wrote it down. And that's why I'm going to do this demo. Okay? This is F equals ma for a string. What is d2y dx2? Let's think, if I take this string and I'm going to shake one end of it. Okay? Again, wait a minute. You could see it if I were to go like over here. This is a horrible idea. I love horrible ideas. I love it. Now you're actually going to see it for the first time. Oh my God. I'm going to catch myself on fire. It's going to be right down your alley. It's going to go over your head. I hope I'm tall enough. Yes, this will be beautiful. Now everybody gets to see the wave along the axis that I've been looking at it for all these years. It's the first time this demo hasn't sucked. Oh, I'm sorry. All right, so I'm going to shake. Oh, man. Oh, you can't see shit down there. Okay. I'm going to shake this end, and you're going to see this pulse go down. Whoa. Didn't it look cool that way? Still no? Okay. Right? If I shake my hand here, then the disturbance goes down there. I'm shaking in time here, and I'm making a disturbance in space there. Totally worth it. Okay. Let me see if I can not clothesline anyone here. Oh, this was triggering. I'm sorry. Okay, so now you saw that. So what we got to do is think about what these two things mean. And this is the curvature. Right? So your hand holds the string, and your hand moves up and down like this. And what does that do? It makes the string, the string do that. Okay? So this is d2y dx2. Right? If you were to plot y versus x, and if it's flat, it doesn't have any curvature. It has no second derivative. If it's a line, it doesn't have any curvature. It has no second derivative. It has a first derivative if it's a line. But if it's curved, it has a second derivative, and that's what that is. And if it's curved, it'll feel a force pulling it back to be straight. So that's curvature. So curvature equals if you shake it with your hand. Right? So if I shake one end with my hand, if I give it a d2y dt2, if I accelerate it, I generate curvature in the string. Okay? How fast does that curvature move away? The speed of the wave. Right? If I make a sinusoid with my hand, shake it at the sinusoid flies away at some speed, and that's here. The speed is not equal to that, but the speed is related to that. Square root of t over mu. So that's 1 over v squared right there. Right? So all the wave equation says is if you shake one end of the string, it creates curvature in the string, and it runs away at 1 over v squared, or square root of t over mu. Right? So there's your intuition. Without having to do all the work, you get all the intuition. Well, some of the intuition. Okay. So now what we need, if we're going to do homework problems, that's all been, fun and games and touchy-feely, but we need an expression for the solution. What is the answer? What is y? Okay. So since this is a partial differential equation, it's got 2 second-order terms in it. That basically means a lot of stuff can happen. Okay, if I had to put that in English, that would mean it can do lots of weird stuff. And physically, it can do lots of weird stuff. Right? I hold this string, I can shake it all kinds of ways. Right? So we're going to talk about different kinds of waves. So one is a traveling wave. All right, this is the first one. So this is basically a type of solution to the wave equation. But it's also a type of motion of the string. Okay? It's a certain way that it moves. So we are going to go back to D. We're not going to call this Y. We're going to call it D because I want to match the book. Okay? So I'm just going to say D equals Y. It just means the vertical displacement. Okay? Just so this matches the book so you know what I'm talking about. So D is a function of X and T equals the displacement, vertical displacement. Well, it doesn't have to be vertical, but whatever. The displacement. All right. So it's basically just a sinusoidal wave going to the right. Let's go ahead and just write it down. The solution looks like this. An amplitude, you can imagine a sinusoidal wave going down the string has an amplitude. Sine, you can probably also imagine it's sinusoidal as it goes down the string. And here we write some funny letters. Kx minus omega t plus phi. Right? That is a traveling wave. Okay? So let's talk about what all those things are. Real quick so you understand how to use it. All right, so I guess if I had to draw it, if you want a little drawing of what this looks like, you would say that here's the displacement of the thing as a function of position. So you can see if you were to do a snapshot in time and make a function of position, that you can make t equals 0, it's just a sinusoid. It's sine kx plus phi. So you could say, okay, it looks like this. It's some snapshot in time, but it's also moving because of the time dependence. So it's not really a function I can draw, right? It's a function that moves in time. So you could draw it that way, or you could also draw it this way. You could also say, plot it versus time, and let's watch one position. This was a snapshot in time over here. Because I plotted it versus x. Now I'm just sitting on one part of the wave as it flies by and watching it go up and down. Right? All of these are up to amplitude A, and one is versus time and one is versus position. Okay, here we go. I should start doing these in groups. Okay. Okay, so let's look at some properties of the wave. Now that we have these two plots, in our head we see it flying by. Okay. So one that you might know from your youth is when you take a snapshot in time and you look at it, what is the difference between this position and this position? The wavelength. You may have heard of the wavelength, right? But we don't see the wavelength in here, do we? Trouble. If you just watch one position in time, watch it fly by, this is the period. Just like an oscillator, you would call that the period t. Right? Period in seconds, and this is the wavelength in meters, say. Lambda. Oh, no. Wavelength in meters. You've probably heard of a wavelength before. Let's see. Why does it say A and D on the y-axis? So D, this is the displacement. This is the label for the axis, and A is the amplitude. So it's the D-axis, and A is the amplitude. So the D is on top and the A is down below. It's also going to negative A if we want to just make it more complicated. There you go. And this is 0. There you go. Okay, so you're okay with T. T is the period. F is 1 over T is the frequency in hertz. And I think you're even cool with omega, which is 2 pi over T, which is the angular frequency in radians per second. Okay, you love those because we did them for circular motion. We did them for harmonic motion. The same thing for a wave. What you probably aren't going to like is applying those radian ideas to space. Yeah, so we got to apply the idea of radians to space. Okay, so let's go. We're going to follow the same procedure here. Lambda is the wavelength, like I said over there, in meters. Let's skip this one and write something called K. K is 2 pi over lambda. Okay, it's the wave number. And it's just how we describe the wavelength when we're writing wave equations. Okay? But there's a reason we do it this way. It is literally the number of waves per radian. Okay? Just like just like over here we have radians per. I'm sorry, it's the number of radians per wave. Sorry. Okay, because we multiply it here, it's radians per meter. And this is in meters, and we end up with radians. Just like here, this is radians per second, and this is a seconds, we end up with radians. Right? So it is the wave number, it's the number of radians per meter. But the reason it has the word wave number, what it really means is, you can work this out. If you were to go for a meter, it tells you how many waves fit in a meter. Right? Just like how many waves fit in a second, how many waves fit in a meter. Right? That's what this idea is. So it's just because we don't want to write 2 pi over lambda here all the time. Okay, so that's why we have this thing we just call K. If you want, you can write 2 pi over lambda over and over and over again. But I want you to get used to the idea of a wave number. So it's just the radian version of wavelength, just like you have a radian version of time. Okay? So there you've got all those parts. So, oh, look at my last, look at this. Oh, we're done, right? I ran out of notes. It sucks. God, it's such a rough day, I'm telling you. All right. Now, so we're going to start using this next time. We're going to use that solution and whatever we're going to do. Class is over, yes. Yeah, no, X is an independent.